end as an introduction to a very simple case of mirror symmetry. Mirror symmetry is about a comparison between two kinds of geometry. So I will first start with an introduction to geometry for non-mathematicians. When non-mathematicians think of geometry, they usually think of what is now called Euclidean geometry. Euclidean geometry was created by Euclid in 300 BC and written down in a series of 13 books called the Elements. The Elements were the first attempt to develop geometry from first principles. This resulted in one of the most successful textbooks ever written. The originals did not survive, but since their first printing in 1482, there have been more than 1,000 editions. The picture you see here is a famous fragment that is dated about 100 AD and which contains the statement of a single proposition. Euclid deals with familiar concepts such as points, lines, lengths, and angles, and proves that these have the expected properties. The Elements were written in modern mathematical style, with axioms, definitions, theorems, and proofs. The axioms, from which everything else starts, were regarded as self-evident truths. It should be said that this is very different from modern mathematical thinking, in which axioms are regarded as independent of any external reality. The actual application of mathematics to science comes from matching the axioms to the concepts in the real world. It would be nice if reality were indeed described by Euclidean geometry, but things are not that simple. For example, the Earth's surface is a sphere, so it is not described by Euclidean geometry. Indeed, if we draw a triangle on the surface of the Earth, then the sum of its angles will be more than 180 degrees. Of course, one can say this is cheating, since the Earth is embedded in 3 space, and it is really in 3 space that one should do Euclidean geometry. But this does not work either, as Einstein taught us. Indeed, he described the universe as a 4-dimensional space-time continuum which is curved in the same sense that the surface of the Earth is curved. Now it turns out that Einstein's theory of general relativity is itself incompatible with quantum mechanics, and string theory is one attempt at solving this. String theory is a model for physics in which particles are represented by vibrating strings. To do this properly, one has to enhance 4-dimensional space-time with yet more extra dimensions. For example, one model of string theory would require 6 extra dimensions, which are in some sense curled up. The picture you see here is a 2-dimensional cross-section of such a 6-dimensional curled up space. Here is an example of a curved space at a place where you might perhaps not expect it, namely in art. This picture by Escher is best interpreted as a picture in something called the hyperbolic plane. So what is the hyperbolic plane? We have seen that the axioms used by Euclid were supposed to be self-evident, but even so, among those axioms there was one that was considered by many to be less self-evident than the others. This was the so-called fifth postulate, which posits that through a point outside the line, there is exactly one line parallel to the given line. Over the centuries, people unsuccessfully tried to prove these axioms from the other axioms. Ultimately, it became clear that this is not possible, and this led in the 19th century to the development of elliptic and hyperbolic geometry, in which the fifth postulate is replaced by a different axiom. To understand the picture circle limit 3, which I just showed, it is best to look at a much older Euclidean analog also by M.C. Escher. We see that the Euclidean picture is preserved by translating in a number of directions. So I'm just indicating some of those directions. It turns out that the regularity of the picture circle limit 3 may be explained by a similar kind of translation invariance, but now in the hyperbolic plane. It turns out the picture is drawn on something which is called the Poincare disk model of the hyperbolic plane, which should be thought of as some kind of map or chart of the latter. It turns out that the rows of fishes are preserved by hyperbolic translations, so there are many of those rows. They're preserved by hyperbolic translations, just like the reptiles in the previous picture were preserved by Euclidean translation. Let me add a final comment to this. If you are not from the Netherlands or Belgium, then perhaps you do not know the work of M.C. Escher. In that case, you should definitely check it out. There are many intriguing works, and they often have a highly non-trivial mathematical story behind them. Okay, so we talked about curved spaces, but how do we describe curved spaces? Well, it turns out that like real-world cartographers, mathematicians use the concept of charts and atlases to describe the spaces they use. Here you see a typical world map, and it is well known if one uses one map for the whole Earth, then there are enormous distortions near the poles. What is even worse is that the poles are not even represented by single points. They're spread out. So such a map is basically useless near the poles. It is of course known how to solve this. One should use different charts which overlap each other. And a collection of such charts is called an atlas. And here you see part of an atlas of the Earth. And note in particular that now I have a chart or a map of which properly represents the South Pole.
Wacht, hoor me nu?
Yes?
Oops.
Excuse me?
No, sorry, that was a mistake.
The surface of the Earth is just an example of a two-dimensional sphere, about which we will be talking a lot. So here is a convenient atlas for a sphere with two charts. One chart covers the northern hemisphere, and the other chart covers the southern hemisphere. And there is an overlap near the equator. Note that people living on the two charts will view the equator differently. To illustrate this, I drew some little men on the equator. The people on the southern hemisphere are seeing these little men upside down. This will be important for us later. After the invention of hyperbolic and elliptic geometry, mathematicians became aware that there are in fact many different kinds of geometry. And the concept of an atlas yields a convenient way to talk about just geometries. One specifies a geometry by saying what kind of coordinates are allowed on a chart and what kind of coordinate changes are allowed if we move from one chart to another. The spaces which occur in such geometries are often called manifolds. Real manifolds, and these are the most common ones in real life, they are described using charts whose coordinates are expressed in real numbers, and the coordinate changes are given by something which is called smooth functions. Complex manifolds are described using charts whose coordinates are expressed in complex numbers, and the coordinate changes are given by holomorphic functions. I will not define what holomorphic functions are. It will be sufficient to know that holomorphic functions are extremely rigid. It is enough to know them in a very small set of points to know them everywhere. Physics uses the language of symplectic geometry. At least this is one of the languages they use. And in symplectic geometry, or in the way physics uses it, for example, a one-dimensional particle is described by its position coordinate and momentum coordinate. And coordinate changes should respect something which is called a symplectic form. The difference between these geometries lies not so much in the kind of numbers they use, but very much in the nature of the coordinate changes. Smooth functions are very flabby, and hence so are real manifolds. Complex geometry, on the other hand, is very rigid because holomorphic functions are very rigid. Symplectic geometry is in between, but much closer to the real side. In the next slide, I will discuss a very simple example in which all these geometries appear. I apologize that this will be a bit more mathematical than most of my other slides. So what we will be considering is subsets of the complex 2 space. So 2 complex coordinates, but you have to remember that a complex number is itself 2 real numbers. So this is actually the same as real 4 space. And the subsets we will be describing by a single complex equation. But again, a complex equation has a real and an imaginary part, so it's actually 2 equations. So the E lambda, which we describe here, they're described by 2 equations in 4 space. So they're actually surfaces. They're 2-dimensional objects. Now the complex 2 plane obviously has a complex structure. Its coordinates are expressed in complex numbers. But then it also has a real structure, which is given here. And it turns out that it also has kind of an obvious canonical symplectic structure. And all these structures are induced on the E lambda. So let's first look at the real structure. It turns out the real structure is independent of lambda. So how this surface looks like is a torus. This is a torus with 1 point removed. But one should really think of this point at infinity. And that's why it's drawn like this. So this is supposed to go off at infinity. And this object is called a punctured torus. As I said, E lambda inherits, in addition to the real structure, a complex and a symplectic structure. And it turns out that the E lambdas are all different as complex manifolds. Well, for generic values, they're different. On the other hand, if you consider the symplectic structure, then they are all identical. So what we should retain from this example is that symplectic manifolds are somewhat resistant to deformation. Indeed, varying the parameter lambda may be viewed as deforming. This deformation invariance is a very important property of symplectic geometry, which does not at all hold for complex geometry. Now, at one point, string theorists discovered that the spaces they used admit a strange kind of duality. Like in the example we just saw, these spaces have both a complex and a symplectic structure. Remarkably, it's seen that every such space has a mirror partner, such that its complex geometry corresponds to the symplectic geometry of the mirror, and vice versa. And this was the birth of mirror symmetry. So physicists like to do experiments. So here you see a typical table of 7,555 spaces within a certain class, in which each space is partnered with its mirror. The spaces are depicted using certain invariants on the horizontal and the vertical axis, and you get the mirror partner of a space by reflecting across the vertical line through 0. So the spaces are represented by points, and if you have a particular point, you find the mirror partner by reflecting across this line. The first applications of mirror symmetry were enumerative, and they were based on the principle that some computations can be done conceptually more easily on the other side, on the mirror. Then came Maxim Kontsevich, who made the sweeping conjecture that mirror symmetry should be liftable to a much higher level. This conjecture became known as homological mirror symmetry. For those who don't know, Maxim Kontsevich is a very famous mathematician, and here you see him talking in front of a blackboard, which is what mathematicians like to do. Concerning mirror symmetry, I should say that in complete generality it remains conjectural. However, many cases are now known, and the number of such cases is essentially growing by the day. So this ends my introduction. The idea is now to give some vague idea about what homological mirror symmetry has to say. Unfortunately, this is very difficult, as the language needed to even state homological mirror symmetry is highly advanced. So what I will do instead is to explain a simple example. I will explain what mirror symmetry has to say about holomorphic vector bundles on the two-dimensional sphere. This is something that can be explained relatively easily. Now, since this talk is supposed to be accessible for non-specialists, I will first explain a bit what vector bundles are and give some examples in simple cases. Well, I know that most people in the audience know what a vector space is. In any case, the precise definition is not so important. Let's just say that's a kind of space in which you can add points and scale them. Now, informally, a vector bundle is a collection of vector spaces parametrized by a space. And here you see two artistic impressions of vector bundles. You should think of these pictures as stretching out to infinity. The picture on the left is a collection of lines, and the picture on the right is a collection of planes, and each of them have their origin marked. And as we have seen, this makes the fibers into vector spaces. There is one non-trivial example of a vector bundle that is easy to visualize, and that is a tangent bundle to a space, which is the union of its tangent spaces. And here is a picture of a tangent space to a two-dimensional sphere. Now, if I move the point, then we see that the tangent space moves with it. So we see that the tangent spaces of a space really form a collection of vector spaces parametrized by that space. So we may indeed consider the tangent bundle as a vector bundle. Okay, so here I give a somewhat more formal definition of a vector space. So we have a total space which maps to a base space, and the fibers of that map, they are vector spaces. And what is not shown on this picture is that the vector space laws, so the addition and the scalar multiplication, should vary smoothly with the fiber, but this is always implicitly assumed. Furthermore, for the sequel, I should say that the rank of a vector bundle, it's actually written here, is the dimension of a fiber. And we will often encounter vector bundles of rank 1, and these are called line bundles, because then the fibers are just lines. Of course, if we have a space, we can always make a vector bundle just by taking the product of that space with a vector space. So that's what I've done here. I mean, I took real numbers to the arc power, that is some vector space, and I take the product. And these objects are, of course, not very interesting. So then the question is, are there other vector bundles? And if so, how would we recognize them if we saw them? Well, it turns out that to recognize non-trivial vector bundles, you can use the concept of sections. A section means that in every fiber, you choose a point. So the blue line represents a point in every fiber. And again, the point should vary smoothly with the point on the base. It should vary smoothly from fiber to fiber. There is, of course, a canonical section where we assign just 0 to every fiber. And this is called the 0 section. And here is a two-dimensional picture, or an attempt at a two-dimensional picture, where I've drawn both the zero section in green and a non-zero section, a section that's everywhere non-zero, in blue. Now obviously a trivial bundle will have non-zero sections. We just take the same non-zero point in every fiber. In fact, for a vector bundle of rank R, being trivial is equivalent to the existence of R linearly independent sections. So now it's time to give the first example of a non-trivial vector bundle, and in fact a line bundle. And this will be a line bundle on the circle. And it's the so-called Mobius strip. So again, the convention is that these lines, these intervals should stretch to infinity, but they should sort of be curl around in the way they're drawn here. So this asks for a little bit of imagination. Now, if we wanted to prove that this Mobius strip was a trivial line bundle, what I should do is produce a non-zero section. So let's try to produce one. So I have to start somewhere. So I'm starting here in a fiber, and I'm going to move from fiber to fiber. Now I can do pretty much everything, but the only thing I'm not allowed to do is to cross the green line. Because the green line represents zero. And a non-zero section, of course, cannot be zero, so it cannot cross the green line. And we see if we've moved around, we arrive in a point at the original fiber, but on the other side of the green section, so it's definitely a different point. And this is not allowed for a section. So our attempt at producing a non-zero section was unsuccessful. And it's clear if we had started somewhere else, we would have run into the same problem. So we see that the Mobius strip is indeed a non-trivial line bundle on the circle. Let's go back to the tangent bundle. After all, this is the easiest bundle to understand. The sections of a tangent bundle are called vector fields. In other words, a vector field is a choice of tangent vector in every point which varies smoothly with the point. And here I've drawn a vector field on a sphere, and you see that there's something wrong with the North Pole. It turns out that this is not an accident. Whenever one tries to construct a non-zero vector field on a sphere, one will run into trouble. And there's a mathematical theorem behind this, which is called the Hyperbolic Theorem, which states that there is no vector field on a sphere that is everywhere non-zero. And informally, this theorem is known as you cannot comb the hair on a coconut. So in other words, the tangent bundle on a sphere is non-trivial. Now it is said that every lecture in mathematics should contain a proof. So I will try to prove the Hyperbolic theorem for you. And for that, we use the convenient atlas, which we introduced earlier. And our proof will be by contradiction. So I will going to assume that there is a non-zero vector field on the sphere. So I will assume the Hyperbolic theorem is false. So this means there exists a non-zero vector field on the sphere. So I'm going to assume there is such a non-zero vector field, and then I will run into a contradiction. So this means that the Hyperbolic theorem must be true, that there is no such non-zero vector field. Now, a non-zero vector field, if there is one, can be described by a non-zero vector field on the northern hemisphere and a non-zero vector field on the southern hemisphere, and they should agree on the equator. Okay, so let's assume we have a non-zero vector field, and then I'm going to take a map of the northern hemisphere and draw this vector field on it. And I've drawn an example. Now on the right-hand side, I've retained only the things which are on the border, right? And remember, the border actually represents the equator. So this would be the tangent vectors on the equator, but seen from the people on the northern hemisphere. What I'm now going to do is move all these vectors on the equator to the center of the disk. And I'm also going to scale them. And I'm going to start by thinning them out a little bit, because otherwise the picture becomes too dense. And I'm scaling them also to avoid the picture becomes too dense. So I'm moving the vectors, but I'm moving them parallel to the center. Okay. So we see now that the last thing I did is to connect the endpoint of the vectors. And this is the orange curve. And we see that the orange curve does not go around the origin. A priori, it might have been something like this. This did not happen. And this turns out actually to be a general principle for a non-zero vector field on a disk. If I had taken a different non-zero vector field here, I would have gotten a different orange curve, but it would not go around the center of this disk. And I'm actually going to explain why that is. So what I've now done, instead of taking this circle, I've shrunk this circle to a circle of radius 0. But then I did the same thing. I moved this vector to this side, scaled it. Now there's only a single vector, so the orange curve is a single point. If I enlarge this disk, I get an orange curve here. But we see the orange curve can never cross the center, because if that would happen, we would have a 0 vector here, and that 0 vector would come from this side, but on this side there are no 0 vectors because it's a non-zero vector field. Okay, so we understand what happens on the northern hemisphere. Let's now look at the southern hemisphere. So recall the people on the southern hemisphere, they saw everything on the equator upside down. So this means they're going to see a mirror image of the tangent vectors as seen by the northern people, and mirror image here will mean that it has to be reflected with respect to the circle. So the green vectors are obtained from the blue vectors by reflecting with respect to the tangent line of the circle. Now I can make an orange curve with my green vectors, and now we see that it actually goes around the origin. One has to think a little bit why this happens. The point is, if the green vectors were just obtained by reflection with respect to a straight line, then we would have gotten a simple mirror image. But now we are reflecting across the circle. So somehow the rotation of the circle gets incorporated in the rotation of the orange line. And that's why it goes around the origin. And you can actually, if you think a little bit about this, you can actually understand why it has to go twice around the origin. So we see that the green vectors on the boundary here cannot be obtained from a non-zero vector field on the southern equator. But we had started with a non-zero vector field on the disk. And so we have obtained a contradiction. And so the Hyperbolic theorem is proved. What happens with other spaces? Well, we were working with a two-dimensional sphere. What if we look at a one-dimensional sphere? Well, a one-dimensional sphere is just a circle. And obviously a circle has a non-zero vector field. And that there happens to be a general theorem behind this. A sphere of arbitrary dimension admits a non-zero vector field if and only if it has odd dimension. And this is consistent with what we saw so far. A circle is one-dimensional, hence odd, and it has a non-zero vector field. A sphere, a two-dimensional sphere, is even-dimensional, and it doesn't have any. You can also ask if perhaps when does it happen that the whole tangent bundle is trivial? Well, it turns out that this happens very rarely, and namely in dimension 1, 3, and 7. And this is intimately connected with the existence of the quaternions and the octonions. So for the people in the audience that know about the quaternions and the octonions, I can explain how this works. So the way to get the vector field on the circle is to embed the circle in the complex numbers, in the complex plane, and then we can get the non-zero vector field by rotating the normal vector field. So the green thing here. And this rotation is multiplication by I. Well, it turns out you can do exactly the same with the quaternions. You can embed the three-dimensional sphere in the quaternions, which are four-dimensional, and then you can construct three non-zero vector fields by multiplication by I, j, and k, respectively. And you can do the same thing with the octonions. Some other examples. Here is a torus. So a torus is a surface with one hole in it. And to specify a point on a torus, you basically have to specify a point on two circles. So you have to specify where it is, like here. And you have to specify where the point is, like here. So a point on a torus is the same as specifying a point on two circles, so we can identify a torus with a circle times a circle. Now, as we've seen, a circle has a non-zero vector field, so the tangent bundle of the circle is trivial, and one can easily deduce from this that this implies that the tangent bundle on this product is also trivial. And indeed, I had no difficulty at all drawing a non-zero vector field on the torus. Surfaces are characterized by their number of holes. This is called a genus. And here is an example of a surface of genus 2. And it turns out that surfaces of a genus different from one do not admit non-zero vector fields. Hence their tangent bundles are trivial. And this is a consequence of something called the Poincare-Hopf theorem, which gives a relation between the zeros of a vector field and the Euler characteristic of a compact real manifold. Vector spaces can be added, and the addition is just the product. So to add two vector spaces, we just take a pair of vectors, one in one vector space, one in the other vector space. Easy to see that this is again a vector space, and the dimension is the sum of the dimensions. We can do the same with vector bundles. We just define the addition fiber-wise. And this is part of a general principle. Every operation on vector spaces can be defined for vector bundles by performing the operation fiber-wise. For example, there is also a product of vector spaces called the tensor product, and a similar operation exists for vector bundles. Let's go back to the circle. We constructed a non-trivial vector bundle on the circle, the Mobius strip, but of course we also have the the trivial bundle, which I will denote by O. And it turns out this contains enough information to describe all vector bundles on the surface. They're either trivial or they are trivial plus the Mobius strip. So this tells us almost everything we need to know about vector bundles on the surface, except that there is a maybe a little bit surprising relation. If we add the Mobius strip to itself, we get a trivial vector bundle. And I will explain this also. And to start the explanation, I should tell you that the Mobius strip is actually embedded in the trivial bundle on the circle. And I'm going to demonstrate this in animation, but I'm only going to animate the fibers of the vector bundles, because otherwise the picture becomes too dense. So the Mobius strip will be red, and the fiber will be this line, and the trivial bundle will be the square. Again, this is supposed to stretch out to infinity. So now we moved over the base, and then we see that the fiber of the Mobius strip has to rotate, but the trivial bundle, the fiber remains the same. So we see that the fiber remains nicely embedded in the trivial vector bundle. Okay. And now I can explain the relation that the Mobius strip plus itself is again a trivial vector bundle. Now I've embedded the Mobius strip twice in the trivial bundle. I've embedded one copy horizontally and one copy vertically, but it's the same Mobius strip, just differently embedded. And now if we move, we see that the two copies remain nicely disjoint, and they keep spanning the trivial bundle. This is kind of a fun activity. And for example, one place where this is introduced is in this book, but there is many more things to know. So earlier we saw a classification of vector bundles on the circle. It turned out that there were two indecomposable ones, and you could write any two others in terms of those. One has a similar result in general. However, the number of indecomposable vector bundles may be infinite. And this happens on the two-sphere. This happens on the two-sphere. The list of indecomposable vector bundles is here. So we have the trivial line bundle, and there's a tangent bundle, which has rank 2, which we already saw. And then it turns out that there's actually a more fundamental vector bundle than the tangent bundle, which is harder to construct, harder to visualize, but it's there. And it's a bit, you can view it in various ways, but it's a bit like an analog of the Mobius bundle. And you can see this if you go to higher rank, then suddenly the situation becomes similar to the situation on the circle. The bundle is either trivial or trivial plus a copy of this strange vector bundle. And this kind of stabilization always happens, and it is the subject of something that's called K-theory. Now, up to now, we have been treating the sphere, the two-dimensional sphere, as a real manifold. This is the easiest, but it turns out that it's actually also a complex manifold. It has a complex structure, and this one can say in several different ways. You can use stereographic projection to project it on the plane, and then identify the plane with the complex numbers. So then you get a complex structure outside the projection point, and then you still have to argue that there's a complex structure there. Or you can also identify it by the projective line over C. Anyway, let's retain that the sphere is a complex manifold. Now, if we're on a complex manifold, then let's go back to the definition of vector bundles. So recall that a vector bundle had a total space mapping to a base space, and the fibers were vector spaces. Now, if M is a complex space, then it's natural to require that V is also a complex space, and that the or complex manifold, and that the map to the base is also a morphism of complex manifolds. And if we have this, then we call V a holomorphic vector bundle. And for example, if we start with a complex manifold, and if we take its tangent bundle, then the tangent bundle is always holomorphic. So actually the tangent bundle to the sphere also has a holomorphic structure. Now we can go back to question, what's the classification? Well, the holomorphic line bundles on the sphere are indexed by Z. And if you forget their complex structure, they actually correspond to the real line bundles of rank 2, which I listed earlier. Moreover, what's very nice is that every vector bundle on the 2 sphere is a direct sum of line bundles in a unique way. Excuse me. So there are no strange relations like we had for the circle, where the Mobius strip plus the Mobius strip turned out to be trivial. Okay, up to now we haven't talked about morphisms between vector bundles, but we need them now. Well, again, the principle applies that if you can do a construction for vector spaces, you can do it for vector bundles. Just do it fiber-wise. So the formal definition of a morphism between vector bundles is a commutative diagram like this. This means if you go like this, it's the same as going like this. And if you restrict to a fiber, you should have a map of vector spaces, which is called a linear map. The space of such homomorphisms is itself a vector space. And if we look on the sphere, and we look in particular at line bundles, then there's a formula for the dimension of that vector space. Now, the formula is not so important, but what is important to realize is that we get a finite dimensional vector space. And that is because of the extreme rigidity of complex geometry. If we had taken homomorphisms as real line bundles, we would have gotten an infinite dimensional vector space. Okay, so now we have finally made it to mirror symmetry. So mirror symmetry is going to give us a new way to think about the line bundles on the 2 sphere we identified. So the mirror partner of a 2 sphere is a cylinder with markings on the boundary called stops. And there's also a symplectic structure, which I will not talk about it because it turns out that in this case it's actually not so important. This is the deformation invariance of symplectic structures. The role of the stops will be explained later. Right now they're just there. Homological mirror symmetry tells us that the line bundle ON on S2 corresponds to a curve that goes n times around the cylinder. So I've drawn this O0, the trivial bundle. So it goes 0 times around the cylinder. So I've drawn it by a straight line. Excuse me?
No, I want to.
Excuse me? So the line bundle O1 supposed to go once around the cylinder. O minus 1 goes around the cylinder in the opposite direction. Here is O5, O minus 5, O10, O minus 10, so we can keep going if you would want to. Now, extremely roughly speaking, if we want to compute the homomorphisms from OM to ON, on the symplectic side, this is given by this expression, where here there's something strange called wrapping, and I'm now going to explain the wrapping by an animation. Okay, so this was the wrapping, and well, you probably saw this end moving, but this end actually also moved, but it moved less because we were close to the stop already. And this, the wrapping should end when the curve is actually infinitesimally close to the stops. But of course, I cannot draw this, so it's close to the stops, but not right. Well, not infinitesimally close. And yeah, now we see the role of the stops. They stop the wrapping. If there was no stop, this would mean I could keep on wrapping forever. And in some cases, this would be exactly what you would want to do. I'll give some examples of the principle on the previous slide, so that I have to compute the intersection of the wrapping of the first curve with the second curve. So this space should comes out as two-dimensional. So we expect to find two intersections after the procedure is done. Yep, it worked. We got this intersection and this intersection. Let's try some more. Now we want 4. Again, it worked. 4 intersections. Okay, here is a situation where we expect to find 0 intersections. And it's a little bit hard to see, but the curves are close together. But again, there are 0 intersections. Here again, we expect to get 0 intersections. Oops. Well, it seems it didn't work. Well, actually, it does work. So what happened is that this intersection is actually of different nature of the intersection we had before. And it's a little bit hard to explain in what sense it is different, so I've sort of represented this a bit schematically. But to really do this, you need to incorporate some information which has been suppressed from the picture. Now it turns out that this intersection point actually represents an element of a higher Hom space. I have defined homomorphisms between vector spaces, between vector bundles. Now it turns out that potentially there is an infinite number of higher Hom spaces. In this case, it turns out there's only one, and which is denoted by x1. So I will not define it, but there is a formula for its dimension, and it turns out that this formula gives us 1. So mirror symmetry has found the higher Hom space. There are other interesting non-contractible paths on the cylinder, and I've drawn them in 3 colors. These correspond to so-called coherent sheaves. So coherent sheaves are generalizations of vector bundles. Roughly speaking, you can think of them as having fibers of varying dimension, but one really needs a better language to talk about them. And the language of sheaves, which exists, was invented by Jean Leray when he was a prisoner of war in Austria during the Second World War. And this is a very nice and a bit funny story, which is partially described in Wikipedia. In this case, it turns out that the coherent sheaves correspond, well, the curves correspond to coherent sheaves living on isolated points of the two-sphere. How do we recognize the mirror of a complex space? Well, there are some heuristics, and one heuristic is the SYZ principle by Strominger, Yau, and Zaslow from 1996, and which is mainly derived from physics, so it's not mathematically rigorous. So it says, and very roughly, because there are more things, if we have a complex space, then to get to its mirror, we should consider a vibration to a base, and then to get the mirror, well, it should be a vibration by tori. So the fibers of this map should be tori, and we've already encountered two-dimensional torus, which was a circle times a circle. Well, a higher dimensional torus is just more copies of the circle. And then to get the mirror, you should take the corresponding vibration by dual tori. But note this picture is only true over some subset of the base, because it may be that the fibers on this side degenerate, there may be some bad fibers, and then it's not so clear what to do on the other side. And then a very important part of the SYZ principle is that line bundles on this side correspond to certain sections of this map. So I'll try to illustrate this for the two-sphere. So I've drawn the Lagrangian the SYZ vibration for the sphere, and it's very easy. We just project the sphere on an interval, and you see that the fibers are circles, and circles are just one-dimensional tori. They're the easiest tori that exists, and it turns out that the small circles on this side should correspond to big circles on this side, and vice versa. And you see that as long as we stay like in the regular part here, let's say on this part of the base, nothing goes wrong on this side, consistent with the SYZ principle. But now if we move to the boundary, then the circles here become zero radius. This means that on the mirror, you should have an infinite circle. Of course, I cannot draw an infinite circle, so I had to truncate the picture. But the stops, and this I cannot really explain, they are somehow a reminder that something went wrong with the picture, that things blew up. Now, on the symplectic side, these infinite things are not such a big problem, because you can always, in nice situations, truncate to a finite part. It turns out that in nice cases you do not lose information by this, because the structure near infinity is very nice. So it turns out that we can simplify this picture to a picture of a cylinder, which is what I've done here, and which the picture is what we have been using. And the SYZ principle tells us that line bundles here should correspond to Lagrangian sections on this side, but on a surface, every curve is Lagrangian, so the Lagrangian is not a restriction, so that's why I've never mentioned it up to now. So here is an example of a section, and to make the picture easy, I've just taken the section which corresponds to the trivial line bundle. For the other line bundles, we would have to have more sophisticated sections, as we saw before. I'm going to give some more examples, simple examples of mirror symmetry. If we remove a point from the sphere, then we basically get the plane. We saw this before. We can do this by stereographic projection, for example. Now it turns out that the mirror of the plane, and on the left, there's maybe a bit strange picture of a plane, but you should think of this this side as sort of going off to infinity. And maybe I should have feathered this a little bit to make that clear. But with some imagination, if you view this as going off to infinity, and then you can flatten it, spread it out so that it becomes a plane. So this is my picture of the plane. And it turns out that the mirror is a cylinder with one stop on the boundary. And we can see this from the Syc principle, and that is why I drew the picture in such a strange way. So I drew the Syc vibration by circles. So the left-hand side is still the same as a sphere. So we have to solve this by putting in this stop. But on the right-hand side, there's actually no problem. We have a finite circle. So on the right-hand side, we don't have to put in a stop. Nothing blows up. That's why we get a cylinder with one stop. And this is part of another important principle of homological mirror symmetry, which I think has only crystallized quite recently in the work of Ganatra, Pardon, and Chende, which is called stop removal. So let's go back to the sphere. So we have the sphere, and the mirror was a cylinder with two stops. So on the symplectic side, we removed one stop. And this, I'm not saying something rigorous, but in nice cases, this corresponds to removing something on the complex side as well. So here we removed one point, and this corresponded to removing a stop on the other side. Okay, so then maybe you're curious what will happen if we remove this stop, and I guess you can guess the answer. This part will have to open up, and we will get a cylinder. Indeed, this is what happens. So this was the picture we had, and if we remove the last stop, then here we now get a cylinder without stops. This means if we want to compute Hom spaces, we have to wrap forever, and we will get infinite number of intersections, so infinite dimensional Hom spaces. And on the other side, we have a cylinder minus 2 points, which you can also think of, which is a sphere minus 2 points, sorry, which you can also think as a plane minus 1 point. And the principle is that the mirror of a cylinder is a cylinder. Now, there are other spaces which have this nice property, which are in some sense self-dual. And now I go back to the example I had in the introduction. In the introduction, if you remember well, we had some spaces parametrized by a parameter lambda, which were puncture tori. Now I remove the puncture. So I want to get a real torus without puncture, And to do this, I have to use homogeneous coordinates. So for the non-mathematicians, this is how it works. And then this E bar lambda is a torus. And it turns out that just like the cylinder, its mirror is given by the same real space, namely also a torus. Now, I already did this before, I excluded 2 points, and perhaps you were curious why I did that. Well, it turns out that if I take lambda one of those bad points, we don't get a torus anymore, but we get a pinch torus. So a pinch torus is like a torus where one of the circles has shrunk to 0 radius. And then it turns out, well, something has to happen here with the SYZ principle. So I haven't drawn the SYZ fibration anymore, but it's always by circles. So something has to happen, and it turns out that the pinching is replaced by a puncture. Now this doesn't really look like a puncture. If it were a puncture, it should be something like this. But this would be hard to draw. And as I said, on the symplectic side, you don't really lose information by cutting off stuff that goes to infinity. So I've cut off the puncture and replaced it by a boundary component. So this is this puncture, this picture. If I had more pinches, it's perfectly possible to have these, then each of the pinches would be replaced by punctures on this side. Now I'm going to end with a question. Here we have a boundary component. What happens if we put a stop there? What happens on the complex side? Well, before we were removing punctures, and this meant that we also had to remove something on the complex side. But now we are adding a puncture. This means we have to add something on the complex side. But it turns out you cannot really do this because, well, this space is, in mathematical terms, is compact. This means you cannot easily, in a nice way, add points to it without kind of destroying it. So this doesn't work. Well, it turns out there is an answer, and it turns out that you have to enlarge the complex side in a smarter way, in a more abstract way, and what you get now is a non-commutative space on the complex side. And non-commutative spaces are part of a new kind of geometry, which can no longer be described by coordinates. So one needs a new language once again, and this would again take much more time to explain. So I'll not do it and stop here. Thank you. And I would like to add, I put some references about the things I talked about. These are not all people that worked on mirror symmetry. There are some famous people missing. And even about the things I talked about, I probably forgot some people, so I apologize for that. Thank you.